Hi, and welcome to College Algebra. So the first section we're going to do is P1. This first unit is all the stuff we've covered in previous and Algebra 2 sections, hence the pre-Chapter 1 type deal. So today we're going to talk about real numbers and their properties, some things we just need to make sure we know. So a real number can be used in everyday life, can be physically located on a number line. Something like, 1, 2, 3, or like 0.75, etc. Anything in between going in each direction. Imaginary numbers can't. As you remember, imaginary numbers are when we do the square roots of negatives. That gives us that 2i. We wouldn't see that traditionally. Now there are subsets. Subsets are smaller groups of different things. So for example, when we talk about natural numbers, the natural numbers are things that we could observe in the real world. 1, 2, 3, 4, things we can count. Technically speaking, you're not going to see 0 of anything, but 0 is included in the whole number. Integers are all whole number, include the negatives as well. And rational numbers are any numbers that technically have some sort of pattern. By definition, a rational has to be defined, whereas you can write it as a fraction of two terms, a over b. So for example, all the whole numbers would be, because you could divide them all by 1, and easy fractions like 1/3. So rational would be something like 0.333, etc., is 1/3. Irrational numbers have no pattern. A very popular one being, of course, pi. That 1.0. Pi being 3.14159265358, etc. There's no actual pattern there. The numbers continue forever. That's an irrational term. If you remember back in Algebra 2, we talked about the number e. E is the same way. It's an irrational concept. So let's talk about these subsets of numbers. In general, we're going to focus on all the real numbers. Real numbers can be sorted into one of two categories. They could be irrational, those patterns that don't repeat, so therefore there's no way of breaking them down, or they could, of course, be rational. Now, rational numbers can be broken down into two categories. They could be integers. Remember, integers are just those full numbers, so -2, -1, 0, 1, 2, etc. in both directions. Or they could be an integer, but it is a non-integer fraction. So something like 1 over 2 is a rational concept. It's 0.5. We can rate it as a fraction. But it's not an integer because it's not a whole number. Well, integers, these whole numbers, can be sorted into two different categories. As we said earlier, whole numbers have no negatives. So where do we put the negatives? Well, we'll put the negative integers over here. Okay. And then whole numbers can be sorted into natural numbers, things you can observe in the real world, and of course, 0. Because 0 is still part of the whole number category, but it's not a natural number. So if we were to follow this graphic organizer, for example, I could see that 0 is part of the real number. 0 is a rational. 0 is an integer. It's even a whole number, and of course it's a 0. A natural number would follow the same categories, but 0, if I'm tracing it back up, does not go through the negative integers or the non-integer fraction because 0 is not negative, has no polarity, and it's not a fraction. Okay. Some other concepts, number line is a big one. Location of all real numbers, so everything we can put on here. So every single number that shows up on this graph, like square root of 5, even though it's irrational, it's still technically a real number. So all real numbers appear on here. The only thing that doesn't is imaginary. So no imaginary. Everything else can be graphed on a number line. There's a couple ways we represent graphs. We either do it with an open circle or a closed circle. Open would be like these inequalities, less than or equal to, greater than, or sorry, less than or greater than. Closed circle, less than or equal to, greater than or equal to. Because what the end point, or what the closed means is the endpoint is included in the answers. Open circle means it's not. And then only thing we have to do is consider if we're going to do, or two more things, is whether they're brackets or parentheses. Open circles have parentheses. These ones have brackets. Same reason. The brackets means the endpoint is included. The last thing we would do, of course, is our arrow. So for example, if we were doing something like x is greater than 5, it has no equal to, so I'd have an open circle, and I'd want to point an arrow to everything bigger than 5. So something like this. And then my interval would be, well, I always start with the smallest first. So whenever I'm doing these, I would do small to big. The smallest possible value that comes up is this 5. And it goes on forever, so I would say 5 to infinity. One thing to note, infinities are always parentheses, infinity and negative infinity. You can never reach infinity, so it isn't included as an answer, therefore never has brackets. So let's take a look. Here we have an open circle on the 3 going bigger, so that'd be x is greater than 3, or x is from 3 to infinity. Same thing here. We have a closed circle, so it has to have the equal to value, and the negative 2 has to have the brackets. But it goes to negative infinity. Negative infinity is smaller than negative 2, so negative infinity has to go first, and infinities never have brackets, so that has to be a parenthesis. Now, what if I have two numbers? Well, the lowest number is first, negative 2, and then the second number here is 3. So here we can see that x is less than negative 2 because it's an open circle. We can see that x is less than or equal to 3, so closed circle. So then I would get negative 2 to 3 is where my line is, with 3 having a bracket and 2 having a parenthesis. Here we get a weird one. Sometimes it kind of can be structured like this, but this sort of feels weird mathematically. So something that some people also do is x is less than negative 2, or x is greater than or equal to 3, because saying x is greater than or equal to 3 and less than negative 2 at the same time feels kind of clunky. So we end up seeing that this creates two different situations. Here I get negative infinity to negative 2, so I have to frame that right there. Here I get 3 to infinity. Actually, I put that negative infinity to negative 2. But because those can't interact with each other, they stay separated, and we put a U in there. That means union, or both. It's actually right up here. I think I walked right past it. Union. That's what that's talking about right there. Absolute value. It's the distance between the origin and a number line. Origin, if you want to think about it graphically, is this idea of zero. It's a value of magnitude. It's always positive. Magnitude, as we're going to talk about later this semester, is the idea of distance. For example, I would never run -3 miles. I would run 3 miles in one direction. So no matter what, B minus A always has to be a positive value. Algebraic expression. Oh, let's try one. I think I don't have one. Let's say I had something like 4 minus 6. Well, 4 minus 6 to give me -2, but it has to be a positive value, so that just give me 2. Now, interestingly enough, this creates a situation where, for example, if I do 6 minus 4, I would get 2, and that's positive 2. This creates a situation where subtraction order doesn't matter. Okay. Algebraic expressions, the big things to note are terms, that's each individual thing. Coefficients are always the number in front of the variable. Variable are always our letters, and constant has no variable because it cannot change. So each individual thing is a term. So this would be a term, this is a term, this is a term. We treat them as if plus is happening between them. So you don't write +2, you'd write just +2. Our variable would obviously be the x squared and the x. The coefficient would be every time there's a number in front of one of those variable. So that'd be, in this case, 3 and -7. Now, one thing we can always remember to do is this idea of direct substitution, aka I can just plug those numbers in. So 3 times 2 squared minus 7 times 2 plus 2. 2 squared is 4 times 3 is 12. 7 times 2 is 14. 12 minus 14 plus 2 is 0. And I can do the exact same thing for -2. So 3 times -2 quantity squared minus 7 times -2 plus 2. -2 squared is 4 times 3 is 12. -7 times -2 is +14. 12 plus 14 plus 2 is 28. Some basic rules of algebra. Remember that positive or plus and minus are inverse or opposite operations. They undo each other, just the same as multiplying and dividing. Commutative property just says for multiplication and addition, it just says order doesn't matter, which should make sense intrinsically. 3 plus 2, 2 plus 3. So that if you need something that is order does not matter. Okay. The associative property is very similar. It's almost exclusively for multiplying and adding as well. It means the grouping doesn't matter. If I'm adding 3 things together, it doesn't matter which 2 I add first. Distributive property says that if I'm multiplying on the outside, adding or subtracting on the inside, I have to multiply by each of these things, or I could combine the things in there. The math checks out. The additive identity is specifically 0. What that means is this idea of identity. Identity for both of these things means it does not change. Oops. So what number can I add to anything without changing its value? That, of course, be 0. Same idea with multiplicative. What number could I multiply by to not change its value? That would be multiplying by 1. Additive inverse, that just means two numbers I can add together to give me 0. Naturally, something like 2 and -2. Multiplicative inverse, same idea, but for I need to get to not 0, but I need to get to 1 because 1 is the multiplicative identity. Just like 0 was my additive identity. So something like 3 times 1/3 gives me 1. So what are some fraction properties? Remember, equivalent fractions have to have or be equal. The way we can always check is A times D and B times C, that cross multiplication. Rule of signs. It doesn't matter if you have a negative out front, up top, or down below. If you only have one negative sign, you are perfectly fine. They're all equivalent. People tend to put it out front or up top. The bottom is considered, bad grammar in the math context. 2 negatives is the same thing as having no negatives, which makes sense. Dividing 2 negative numbers is a positive. Equivalent fractions, if I multiply something up top by the same and the bottom of the same value, I don't change it. So for example, 3/4 times 2/2. Well, if I think about it, this 2/2 thing, that's just 1, and multiplying anything by 1 doesn't change its value. Add or subtract values. Remember, you keep the denominator the same as long as you have same denominator. And you just do the operation with the top values, so A plus C here. Multiplying fractions, we multiply straight across. Dividing by fractions, you can either think about it as this diagonal multiplication, or keep your first one, change multiplication change your division into a multiplication sign, and then you flip the third fraction. And then you're just multiplying fractions, so then you just go straight across. Kind of the common way of doing those. Some common things, again, these are just some examples of those properties we talked about on slide 7, including the fractions. It's kind of everything together. Thank you for listening, and I hope you have a great day.